measure the electrical parameters. Then the next C, the next column is simulated the values. You can also have another column of theoretical results. But for the time being, let us focus on the simulation. So we had the first testing point, which you call point A. What did he measure at point A? Class. We did that experiment together, so you have the responses. We should not wait. You have to relate what we drew in theory, and you have to relate what we drew in simulation software. Right? Point A. What should he measure at point A? So DC voltage. DC voltage, but in terms of what? Volt. You have to include the unit. So what did he, what they measure the value? 9 volts. So there's no need to write a V again. Okay? Then we go, the next C testing point is testing point B. What did he measure in testing point B? Pardon? So DC voltage. So DC voltage so DC voltage, simply call it in DC voltage or V, call it VR1. VR1. But this VR1 in terms of volt, because units is very important. What the measured values of potential drop across R1? Pardon? 0.1. 0.21. 0.21. Then point B. Now point C, What the next point is, students? Point C. What should he measure at point C? DC current. Simply, this is total current. What the units of that current? In milliamp. Then what they measure the current? 0.45 milliampere. Are we together? Yes. Then we go, the next testing point is testing point D. What parameter did he measure at testing point B? D? DC voltage. DC voltage across what? So V, the one. In terms of what? Volt. Right? What the potential drops across the ready LED? 2.15. 2.15 volt. Then the next testing point it is what? E. What the measurement parameter? DC voltage. V across second resistor. In terms of 40 volt. What is the value? Hello? 4.49 volt. Then the next testing point it is what? F. DC what? DC voltage. Remember that in case of table of result, listen. In case of normal writing, listen, look on the blackboard. In case of normal handwriting, for instance, you have written here, for instance, that you say that you're just doing the normal writing. You say that DC voltage, whatever, and then you want to mention again DC voltage. You can do, just you can cut like this way, right? So this is in case of the normal writing. In case of the table of results, that's not allowed. Are we together? Are we together? Okay. So what the voltage potential drop across the two? 2.15. 2.1 what? 2.15. The next testing point? G. Then the measured parameter? DC current. DC current. Did we call it current 1 or current 2? Current 2. In terms of 40 milliampere. What the measured value? 0.45 milliampere. Then the next testing point? H. What did he measure testing point H? DC voltage. So V R3. In terms of 40 volt. What the measured value? 60.14. Okay? The next testing point? I. What they measure the parameter? DC voltage. Across 40? That was the 3. In terms of 40 volt. What is it? 0.49. Then the next testing point? J. That the last one? Do you like it? Because it's the last. And J, Adeline, what we are measuring at point J? DC current. Very good. DC current. Noreen will congratulate you later. This is I what? I1 or I2? I1. What its unity? Milliampere. And what is measured value? 0.00. 0 is a good number, especially in digital electronics. Then once you've done it, remember that. So stop writing, stop drawing, and stop writing. Whenever you have drawn a table of result, you must label it, you must name it. So for the table of result, we always name them at the top. For the figures, we used to label them or name them at the bottom of the figure. For the table of result, according to the international standards, it means that you have to label the table of result on top of it. On top of what? Of the table. If this is the figure, we used to say that figure 1, the schematic, right? But in case of table, just you say table 1, then you write its name, but on top of it. Okay? Make sure that you bear it, especially for your project. So let me just use the space. For you, you can write down there. But this is table 1. The table 40, simulation what? Result. Of 40, DC, series, parallel, network. That is all about tables. I told you, or I have introduced you at the beginning, that this is the language of phenomena in engineering. So if you like mechatronics engineering, like to draw tables of results. Not just the tables, tables of what? Of results of the experiment that you have done, whether in simulation, whether in hardware, even in theoretical. So from now onwards, whenever you're doing your theoretical calculation, try to present that, okay, after doing the theoretical calculations about this circuit, what are the results that are formed? Right? If you do remember that what Dr. Jordan Hakim Hosea told you that, we are going to teach you this course in 3 phases. Theory, simulation result, and what? Practice. So when actually, it means that later on, now we can actually navigate on theory and the simulation. But later on, we are going to have another column of practical or hardware measured values. Are we together? Are we together? Yes. So for instance, we can build that schematic circuit having a DC ammeter or DC milliammeter and having DC voltmeter and do the measurement. So it means that here we are going to have another column to see how the simulation results relate with practical results. Because as engineer or mechatronics engineer, you should not always just accept things. You have to challenge. You have to see how do they relate. Are we together? That for instance, the measured DC current at point J, will it be 0 practically or not 0? The measured DC voltage at point D, will it be 2.15 or any other number? Are we together? Are we together? So simply remember that I told you that. And I would like to repeat. When somebody asks you, what is mechatronics engineering? How are you going to answer that question? Possibly you might say that mechatronics engineering, it's a course whereby 50% is all about electronics engineering and the 50% is all about mechanics engineering. That is wrong. When somebody asks you about another question, you are learning or you are studying about engineering. What is engineering? Ask your neighbor, what is engineering? Because he or she studied engineering, but he or she has never think about what you are studying about. So ask your neighbor and ask that question seriously. What is engineering? What do you think about engineering? Do you know the meaning of engineering? Or you're just studying something that you don't have an idea? So when your neighbor gives you his or her definition, note it. Then, once you have finished that question, ask him or her the second question. What is mechatronics engineering? That's the first question which you should learn when you've been admitted to learn about mechatronics engineering. So ask your neighbor, please. What is mechatronics engineering? If your neighbor cannot answer that question, tell him or her, I give you the homework. And tomorrow you have to submit the result. So Maya, you don't ask your neighbor. And Sumaya's neighbor, you didn't ask Sumaya that question. It's a very simple question for her. Ask her again. Now she has a response. So, did you find a definition of what is engineering? You can have a number of definitions. But engineering has a simple and a tangible definition. Mechatronics engineering is also, it has a simple and tangible definition. So, should I help you or should I leave it to you? You like to be helped here, but you didn't help your neighbor. Okay, so write down. So when somebody asks you about what is engineering, it's not a part of the subject, but just it has come in my mind that maybe I have students who are learning mechatronics engineering, but they don't know what they are learning. Possibly. So I guess that possibly you know, possibly you may not know. But let us address these concepts together, right? So when somebody asks you about this question, so the challenge now it's a marker pen. So when somebody asks you this question, what is, just write down. This is very important in definitions of engineering that for instance, for myself, once I learnt it, I have never forgotten it. What is engineering? Don't take that it's a simple question. You might give maybe even 10 definitions, but all of them are still missing something, right? I know that you know what is science. Ask your neighbor, what is science? In Form 1, we taught you what is science. And by that time, you don't know English if you are from Swahili speakers. Primary school like us. So you've been cramming. Science is a study of, then science is a study of, science, you didn't force in your mind until you have it. Because you know in test 1, midterm test, you will find that question. Then the next question, what is physics? Ask your neighbor, what is physics? Hey. Then the next question, what is chemistry? What is biology? You were expert those days, but nowadays you have been retired. So, you know the definitions of science, but unfortunately you don't know the definitions of what? Engineering. There's a different ways that you can define engineering, but this is the simplest one, which it's a fact. Engineering, say engineering. Say engineering. So engineering is just, it's a purposeful use of science. Full stop. It's a purposeful, what is engineering? Again? That's why we taught you science from standard 3. We taught you science until standard 7. Again, we taught you science from what? From 1 to from 4 for some of you. And others until from 6 for some of you. Right? So why were you teaching you science? Because if you want to study engineering, it's a time to purposefully use the science you've been learning. So ask your neighbor, do you remember the science you've been learning from standard 3 up to from 6? Do you still remember it? So if you have forgotten, then forget also to understand engineering. Simple like that. Ask your neighbor again, do you remember the science we learned from standard 3 up to from 6? How many years have you been learning science? Standard 3, 4, 5, 6, 7, right? 5 years. Plus 6, 11 years. 11 years, it's the age of 40, a child who is at what standard 4 or 3. So it's the age of the child. It's not the age of 40 of the baby. Okay. But engineering, how many years are you going to study engineering course? 4 years. Why? Because you have to learn about it, how to use the science you've been learning purposeful. And what the means of this purposeful use of science? You have to use science to solve real life problems. So if you say that, I just want expert in mechatronics engineering, that is good. Then we ask you a question, what problem do you want to solve by using the knowledge of mechatronics engineering? Do you have a real life problem, unique for you? Or you just say, let me go to DMI and find it there. No, at DMI we don't have mechatronics problem. We have mechatronics problems in the entire, in all 31 regions of 40 of Tanzania. So even from your family, there's a lot of mechatronics engineering real life problems. You did not just open your eyes. You might think that it's a political problem, right? Because we used to throw the problems to the politicians. Okay, so then the next question, then we continue with our subject. What is what? Mechatronics what? engineering. So mechatronics engineering, mechatronics engineering. So can you correct your neighbor's definitions of engineering? Or you did not take a note? Okay. So you balance the equation, eh? Mechatronics engineering, we say that simply is the purposeful use of mechatronics, in bracket, it means that mechanical, and electronics science. That's all. So simply mechatronics engineering is the purposeful use of what? Mechatronics what? Science. Which is what? Electronics what? Science. Which I've taught you in O level and the A level. How about mechanics science? Do you remember mechanics? How many topics does it have? 11 topics. The first one, measurements. The second one, Newton's law. The third one, projectile. The fourth one, simple harmonic motion. The fifth one, uniform circular motion. The sixth one, rotation of the rigid body. The seventh one, fluid mechanics. And the eighth, properties, we call it just elasticity. Ninth, surface tension. 10, kinetic theory of 40, of gas. 11th, okay, so that is all about theory, mechatronics. So as mechatronics engineer, whenever you sleep, whenever you wake up, you have to think about purposeful use of what? Electronic science and mechanics science. If you forgot electronic science, you have to review. If you forgot mechanics science, you have to review. Are we together? Yes. Are we together? Yes. Wonderful. So it means that what I say that, for instance, these capacitors and the resistors, there's a lot of science behind it. Resistors, there's a science behind the battery. There's a science behind the resistor. There's a science behind the semiconductor diodes. There's a lot of them. So we as the engineers, we just take those actually innovated components and connect them logically to solve a particular real life problem. Are we together? Any question about what we have been discussing? Is it clear, students? Is it clear? Okay, so if it is clear, that's fine. So today we are going to focus about AC source. So this is the schematic. This is the schematic. Say schematic. So we are going for the diagrams. I told you engineers all about diagram. Schematic, circuit, diagram of 40 series, parallel of AC power of what? AC, yes. And schematic circuit diagram of AC, okay, of series parallel network. For AC power. Remember that in mechatronics, we have mainly two types of sources of power. The first one, direct current. The second one, alternating current. So in workshop 8, I taught you how you can connect different components in series And the source of power, it's what? DC, right? So today, let us cover, or let us deal with AC. And AC is equivalent to the domestic power. Are you ready for that? So if you are ready, stop drawing, look on the blackboard, please. So always, in the next workshop, I will teach you something about the block diagrams. The next workshop, workshop number 10. And I will teach you the philosophy that we are doing, because I usually used to come with a schematic circuit diagram, which possibly for you, you don't know how did we design it. Right? Right? Yeah. So in next workshop, I will open your mind about how do we think in mechatronics engineering or in electronics engineering. So here we are going to have AC power source. So AC power source. So this is our AC power source. And then we are going to have a network. We are going to have a switch. A single throw, single pole, single throw switch. Then here we are going to have a resistor. Let me just make you familiar. The resistor in this symbol, and this is the junction. And here we are going to have also a fixed resistor. This is called TR1. Then here we are going to have a lamp. This is the symbol for the lamp. And the resistance for this resistor, it's a 510 ohm. And resistance for this resistor, it's a 100 ohm. So this is R2. Here you have 100 ohm. Then here we have another lamp. This is lamp 2. Then we also have another network. So here we have a lamp, and then we have a fixed resistor. At this point, we have a lamp. This is R3. This is R4. Then the resistance for this, it's 1.1 kilo ohm. And this resistance for R4, it is 470 kilo ohm. This is lamp 3. This is lamp 4. Then here we have a connection. So you can see that the network is getting a little bit complicated as long as we move. So this is single pole, single throw switch. And here we have common ground. So this is figure for workshop 9. This is figure 1. The schematic circuit diagram. The schematic circuit diagram of 40 of series, parallel, series parallel network for AC power system. So there it's a schematic circuit diagram which consists of how many components? How many components does that schematic circuit diagram consist of? 10 components. The first one, AC power source. It's called the AC. However, that in simulation it has been called the AC, or it has been called the alternator. The second component, the third component, resistor 1. The next component, that is number what? Number 4. So this is number 4. This one, stop writing, stop drawing. This is number what? 5. This one, this one, 10. So how many testing points can we have there? A lot of them, isn't it? It just depends that what do you need to choose. So just draw that circuit quickly and we'll locate the testing point within the same schematic circuit diagram. Then we'll be discussing the theory and then we'll actual that, because the goodness of this one, we know the theory. Okay. The lamps that you are going to use, I say stop writing, listen. The lamps that you are going to use are the lamps which actual that can turn on with the supply voltage of 12 volt. So the supply voltage for this case will be, so the voltage, the supply voltage will be 12 volt, 12 volt, and the frequency should be 50 hertz. Okay? 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 So the internal, I say stop writing, listen and watch. So the internal resistance of this lamp, if you do remember, because this lamp, we can find it in Proteus library, right? And then in workshop, I think that was workshop 7. Yes, in workshop 7, if you do remember, we measured its resistance, internal resistance. For me, remember, we measured the internal resistance. And we did 2 measurements. The first measurement when the lamp is connected to the circuit, and the second measurement is when the lamp itself. So the result, the simulation result, when the lamp is connected to the circuit, it was ranging or it was varying from 23 to 24. When Asma asked the question, why is it blinking? I know you forgot. And for me, I can't forget. Why is it what? Blinking. Then I gave her a response by actually taking a lamp, just a lamp as a discrete component, and measure its resistance by using what? Ohmmeter. Then its resistance, I do remember myself, I don't know about you, but if you forgot, I remind you. It's the internal resistance of that lamp, which can operate is a 12 volt. It is 24 ohm. If you still have a doubt, refer your simulation or refer your notes. Okay? Okay? Okay. It's a little bit challenge to do the theoretical calculation if we don't know the internal resistance of this lamp, because we don't know what will be the potential drop here. Are we together, students? Yes. Because today we have to link the theory and the simulation. Okay? So the internal resistance here, students, what the value of internal resistance for this lamp? 24 ohm. 24 what? Tell your neighbor 24 ohm. Because your neighbor by next week will forget. Then actually be complaining that I have never heard it. I've never what? I've never heard it. Are you sure? Did he learn it? No. Maybe you forgot. Let me remind you. So we dealt with just LEDs. Okay? Class, are we together? So stop writing, stop drawing. Let us choose the best C or the testing point, right? The first testing point, A. The first testing point, it's this one. This is point A, right? So what do we need to measure? Which instrument should you use? Multimeter. Multimeter. Eh? AC. AC. What will that AC voltmeter measure? What will that AC voltmeter measure? Voltage. Hello. What's that AC voltmeter measure? Which parameter? Root mean square voltage. So this AC voltmeter will measure what? Root mean square voltage of DC source, which we've been told that it should be 12 volt. But also, we have to be sure about the frequency. When we change the properties, the frequency of this AC should be 50 Hz, low frequency. Because you can have a AC signal of 12 volt with 50 megahertz. Say 50 megahertz. 50 mega? 50 megahertz is equal to how many hertz? 50 million hertz. What if we give you 50 millions now? You'll tell mechatronics engineering, bye-bye. And I know, what are you going to do? First of all, you'll open the business. You don't have business skills, you say, I will employ them. If you employ them, they maximize profit from you. Okay? Okay? Okay, today I don't want to choose the testing point. You are the one who is responsible to choose the testing point. Tell me, where are we going to locate our second testing point? Class, I'm talking to you. Between the switch and the resistor 1. This one. What are we going to measure? Total current. Let me help you because I know that you're not here. And hence we are going to use what? AC milliwatt milliammeter. So let us take this point as point A, point B. Are we together? The next testing point. So this one. This will be testing point C. So V across R1. What will AC voltmeter measure here? Root mean square voltage drop across resistance 1. Right? Next, see another testing point quickly. Resistor 2. Okay, you like resistors? Ask your neighbor, do you like resistor? Again? So we can measure. So this is testing point what? D. Here we are going to have what? E. V across lamp 1. Root mean square voltage across lamp 1. Then, root mean square voltage across lamp 2. This will be testing point what? E. This is what? A. F. Are we together? Another testing point? After? After lamp 1. Very good. Clap your hand for him. Because he spoke loudly with confidence. Because, you know, some students here, they say, okay, we are done with this. No, we didn't measure current. In power connection, current is not the same. Right? Okay. So if that's the case, wonderful. We'll connect our milliammeter here. AC milliammeter. This will become point 30. A, B, C, D, E, F, G. Then here we are going to connect what? Our milliammeter. AC milliammeter. This becomes 20 H here. Then for this case, you just duplicate. Do we have any testing point here? Adeline, what are you doing? It's not the time for drawing. Today you start with the wrong neighbor. Okay, so why should you not have a testing point here? We have it, point B. What we measure in point B? The magnitude of the root mean square currents at this point will be the same at this point, will be the same at this point. Are we together? Okay. So then we need the duplicate. Okay, so now let me just work myself because you have understood. Because what you have here, this is the copy of this one. But resistance of R3 and R4 is not the same with R1 and R2. So we are going to get different measured physical quantities. Are we together? Ask your neighbor, is mechatronics engineering beautiful to you? Ask your neighbor, is mechatronics engineering beautiful to you? So here we have 40 VLO3. So you can draw it quickly. You can draw because now I just know that what you'll mention. So HI, this is I. We are going to have another testing point here. V across R3. This is what IJ. Right? Then there's no any formula. Here we are going to have another one. This addle will be 20 A I J K. Also here we are going to have another J K L A B C D menopy. So we are about menopy. Then we have another one. V across R4. Then we have another one. So this is testing point 20, L. And after L, JKLM. Those days we used to call it Elomeno. So this will be O. O. So A, B, C, D, E, F, G. You forgot? So R, L, O, M, N. Before O, it is N. So how many testing points do you have there? 14. Is it true? You are still counting. Okay. So when you are done, tell us. Okay, so once we have that schematic circuit diagram, we can do some work in theory. This isn't? We can do some work in theoretical. This isn't? What can we do? You can also have another testing point, which is between this point and this point. Because you learned that when resistors are connected in parallel, the potential drop is the same. You remember that? It's better to verify. Right? You may also have another testing point between this and this. Right? What do I mean? I mean you can have another testing point here. This is V. You can call it V1. Then this one, it's what? V2. So it's just the matter of AC what? Voltmeter. If the source is AC like this one, and then you are going to use AC voltmeter, just DC voltmeter and DC ammeter to do your measurement, then you are completely wrong. That's why you have to understand the schematic circuit diagram that you've been given. Class, are we together? So draw it quickly. So, the theoretical calculated values at testing points. I told you that the point for this workshop 9 is not just to give you the schematic circuit diagrams and then draw it in the simulation software. That's very simple business. The point is to have in your mind, what are you going to measure? Right? Are we together? So in case the simulations give you wrong results, you don't need Olenjolain to tell you that those results are wrong. You just tell yourself. Okay? Are we together? So let us start with the first test. We ended it. So this is N. N, O. Then this is what? P. Where is P? This one. Okay? A. Simply, what are we going to use? Ohm's law. Recall what? Ohm's law. Say Ohm's law. Ohm's law there, we say what? Supply voltage is equal to voltage across O of V1 plus V2. Isn't it? Okay. So Vs is equal to V1 plus what? V2. We don't know the potential drops at this point. We don't know the potential drops at this point. Okay? Then, what do we say that? But this is parallel connection. And this is a parallel connection. The summations of parallel connections and summations of these parallel connections make series connection. Are we together? So simply, what do we say? That supply voltage is equal to current times what? Let's say R equivalent to 1 plus what? I times R equivalents 2. Right? Current is constant because this series. This is parallel, but if you combine series, and this is series. Right? So we have I, and we have what? R1 plus what? R2. This is RE1, and here we have RE2. So supply voltage is equal to total current, then RE1 plus what? RE2. This is question 1. Mechatronics, engineering is purposeful use of what? Of science. In science, you have been learning stuff in this way. Are we together? So this is the first step, because you have to follow steps. The second step. So the second step, we say that let us calculate what? Let us calculate RE1. Right? How do we get RE1? RE1, we say that we'll be having R1 and what? And the L1 parallel with R2, L2. Resistance of L1 and L2. Do you agree? So this is equation 2. Mathematics is beautiful. It's application of mathematics. You should not bother yourself and worry about the lamp and whatever. You just use the theories. And these are the simple stuff for you. Okay? Okay? So then let us find the R1 parallel to L1. So this one will be what? R1 times what? L1 of R1 plus L1. So we say L1, we means resistance of the lamp. Right? Class, are we together? And what the resistance of R1? 520 and 10. What the resistance of L1? 24 ohm. Right? Then we have 40, 510 plus 24 ohm. What do you get? Use your scientific calculator quickly. Give me the value. So that is R1, L1 in series, in parallel. Oh, I made a mistake here. Thank you very much. Clap your hand that you discovered your teachers made a mistake. Clap your hand. So, the lamp 1 and R1 are in series. So it is what? R1 plus what? L1. 510 ohm plus what? 24 what? Mangoes ohm. This makes what? 534 what? Ohm. Right? Then R1 in series, R1 or R2? R2, L2 in series. This is equal to R2 plus what? L2. What is R2? 100 what? Ohm. Plus what? 24 ohm. And what do you get? 124 ohm. Right? We have these values, substitute in equation 2. Then we have what? R of E1 is equal to what? 534. Now you are no longer talking. Why? Because you are busy writing. 124 over what? 534 plus what? 124. What do you get? $163. 163. 163 ohm. Very good. So this is equivalent resistance C1. Right? Huh? So this one we can call it equation what? Equation 3. So I need this systematic. So I want to clean there. Can I clean? Or you are still copying? Okay. So we have the R, the equivalent resistance for this network, the total resistance, right? Then now we are going for what? R, what? R2. RE what? RE2. So RE2. RE2 is equal to what? R3, L3, parallel with what? R4, L4. Right? This makes equation what? 4, Good. Then how do you get R3, L3? R3, L3. What is R3? 121 kilo ohm. Change into ohm because you are going to add ohm and the kilo ohm and ohm. 1,100 ohm plus what? 24 ohm. Check your previous calculation. I know you took 1.1 kilo ohm plus 24, so you have what? 25.1 ohm. Those are the common errors students used to do. You can add a kilo ohm and ohm without changing and make them the same what? Unit. Right? Yes, because you might say that adding. You just add it from your brain. 1,124 ohm. Then R what? R4 L4 is equal to what? R4 plus what? L4. R4 it is what? 470 what? 470 ohm. Zero, zero. So 470,000 ohm. Plus what? This makes what? 470,000. 24 what? 24 ohm. Right? Then substitute in equation 4. RE2 is equal to what? So this is equal to what? Okay, these are in parallel. So it's equal to 1,124 ohm multiplied by what? 470,024 ohm divided by 1,124 ohm plus what? 470,24 ohm. That makes what? 11. 3 to 1. 3.20. 11.20. 11.21.32 ohm. Hello? Where are you going? To do what? So then, we have the value for RE2 and RE1, right? Yes. We have to substitute, so we go to the next step, which actually will be the first step. We say that let us substitute. Let us substitute RE1 and the RE2 in equation 1. Right? So then, what do we say? Remember that we are just calculating the second parameter, the total current. Right? Yeah. So total current is equal to what? Supply voltage over RE1 plus RE2. Supply voltage is what? 12 volt. RE1 is what? Students, RE1 100.68. 100.63 plus 1,121.32. Give me the response. What the current? 0.9. 0.9. So remember that this is volt and this one is in ohm. 0.98 ampere. Milliampere. Ampere or milliampere? Milliampere. So this the current will be flowing in test point B, test point what? P, test point what? Yes, this is still P. That is the total current flowing through the circuit. Okay? Okay? So in our table of result, we will be having how many columns? 4. The first one, testing point. The second one, measure the electric parameters. Or before measure the electric parameter, you should have calculated the value. That's the second column. Calculated the values. Right? The third column, measure the electric parameter. The first column, simulated the values. Are we together? Yes. That's the point where we are heading to. Tell your neighbor, that's the point where we are heading to. And tell your neighbor, don't you drop on the bus until we reach the last destination. Then, so we know, it means that we have the calculated value for point A, it is 12 volt, right? Point B, it is what? 0.98 milliampere, right? And now, what can we do quickly? We can compute the potential drops across point O. Right? Right? Class. Right? We can compute. So the fifth step. We can compute it. We can compute V1. Right? V1 is equal to what from Ohm's law? Total current times what? RE1. Okay? Okay? Total current is what? 0.98 exponent negative 3 multiplied by what? RE1 100.63. What do you get? Calculate it quickly. Also, you can calculate V2. Yes. This one. 9.8 milliampere. Is it 0.98 milliampere or 9.8 milliampere? So, Mavumba has done a Mavumba. But he tried. So we appreciate. Thank you very much. So the value of current is 9.8 milliampere. So here we have what? 9.8 exponent negative 3. Is it correct? Class, are we together? Are we together? Eh? Are we together? 9.8 exponent negative 3. Multiplied by what? 1,121.32. Give me V1 is what? Multiplication by using the scientific calculator. Simple multiplication. Simple multiplication. Like that one. You are still late. Why? 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 What is V1? A? Pardon? 0.987. A? 88. 86 volt. Good. 3 decimal points are important, just enough. Then V2. V2, quickly. This is beautiful science, electrical science. V2. 9.8 exponent negative 3 multiplied by 1,121.20. You don't have even a calculator. You forgot it at home. But during exam, you'll have it. In class, no. What did he find? 10. That is 1. 1,098.89. Okay, 1,098.89 volt. No. That is completely wrong. How can you have 1,098.89 volt from 12 volt? Why is the supply voltage 12 volt? That is the voltage or calculation from the Bongo land. Okay. But he tried his level best. At least he mentioned something. Not like you who has kept you quiet. 10, Point 20? I know that he might be forgotten this one. Those are the common errors. It's 11. 11.01 volt. 10.8 10.989 volt. Hello, keep quiet please. So now we have also the values, the calculated values for the other two testing points. V1 is for testing point O. V2 is for the testing point P. Right? So, what are we still lacking? C. We want to know about C and D and E and F and what? And G. It's a lot of work, No, you have to love them. So we know the potential drop here. Right? Once you know the potential drop, how can we calculate VR1? Macera. We can call this one as I total, and this one can call it I1, and this is I2. And here it is I total. Right? So V1 is what? I1 times what? R1. So how can we calculate it? The same. The same what? V1 is equal to what? How sure are you? Remember, they are parallel. Remember the resistance. Here it's not equal to this resistance. It's not equal to this resistance. It's equal to this. Remember the potential growth depends on the resistance. So do you think that VR1 is equal to V1? So, how can we calculate? It's not difficult. The potential drop from here to here, it's V1. You have to calculate I1 first. How can we calculate I1? Simple. We take the potential drop divided by R1 plus L1. Are we together? Once you have I1, you can calculate VR1, you can calculate VL1. Does it make a sound? So can I clean this part? Okay. You should not be bothered because this is what you've been doing for almost 11 years. So that is all about parallel and series connection. Okay, so we are going for the 60 step. Stop murmuring, please. The 60 step, we say that, listen, V1 also is equal to what? Is equal to V R1 plus V L1. Do you agree? Do you agree? Potential drop from this point to this point, it's V1. Right? So it means that the summation of VR1 and VL1 will be equal to V1. Not VR1 equal to V1. I know that it will be challenging. Because if we did the simulation, you could not even challenge yourself. You just measure and then you don't bother. But if you do the theory behind the calculation, then you can see that some of the stuff are challenging there. Because you know that if the resistors are connected in parallel, same potential drop. So it will be the same. This one will be equal to this one. V1 will be equal to VR2 if we don't have this part. Hello? Let me repeat. I know that it has been a challenge even for myself. When you connect two resistors in parallel, the potential drop across them is the same. But currents is different. Right? So please listen and look. Check your neighbor. Tell your neighbor, look on the blackboard. Tell your neighbor, look on the blackboard. Some of your neighbors are still looking down. Listen. V1, theoretically, V1 is not equal to VR1. Right? V1 is not equal to VL1. V1 will be equal to VR1 if we don't have this network of the lamps. V1 will be equal with VR2 if we don't have this network of the lamps. Right? V1 will be equal to VL1 if we don't have this network. V1 will be equal to VL2 if we don't have this network of resistors. That is according to theory. Am I right or am I wrong? But remember that V1 is equal to VR1 plus VL1. V1 also is equal to VL2 plus VL2. Okay? But remember, resistance are not the same. Currents will not be the same. So the potential drops at this point will not be equal to this one. Will not, for this one will be equal because of the same resistance. Right? Yeah. So remember the theory and use it. So V1, which you know, is equal to what? I1 times R1 plus I1 times L1. Or resistance, let's say that resistance of L1. Because you can confuse L with inductor. Right? I is common. This is I1. So I1 is common. We have what? R1 plus R L1. Right? So we can use that equation to find what? I1. I1 is equal to V1 over what? R1, RL1. Right? Eh? Mavumba, what is V1? 0.986 volt. Here we wrote 0.986 volt. Okay, fine. Even that one is fine. R1 is what? Eh? What? 24. What do you get? Oh, that calculator has been opened as a PCM or a PGM or the EGM student. Pardon? 1.85 what? Milliampere. 1.85 volt milliampere. That is what? I1. Are you together? So we compute. So that is measurement parameter what? This is the measurement parameter in which testing point? Point C. Tell your neighbor we have now there calculated the value of point C. Your neighbor is quiet and even yourself is quiet. So for us who have been living in Bongo, we say the match is draw, right? Then once we have I1, what can he also determine? This is measure the parameter for point C. You are lying. Salome, that day, this is the measurement parameter for which point there? Salome has been confused. My friend there? Point G. This is a current I1. I1 flowing through R1, flowing through lamp 1. And then here we have what? AC milliammeter. So this is the measurement parameter for point G. Because now you have been confused. Because at the beginning of this circuit, you saw this circuit is very simple. That circuit is very simple. That is primary school circuit. Okay, fine. So let me write the points to remind you, because I know that it's very easy for you to be exhausted and confused. Because the assignment I will leave to you, you draw the table of result. Is it clear? So you can calculate the potential drops across R1, which is point C. Right? How? So 7th step. So the 7th step, now we are going to compute it. compute V R1 and what V L1, right? V R1 is equal to what, my dear student? I1 times R1. I1 is what? 1.85 exponent negative 3 multiplied by what? R1. What is R1? 510 ohm. What do you get? Then VL1. VL1 is equal to what, Patricia? What the formula of VL1? I1 times what? Resistance of lamp 1. Right? Do you enjoy? Okay. So I1 times what? RL1. Okay? Next C. What is I1? 1.85. Some of the students, they are just watching me. They are just watching. I just ask them the questions, which are very simple. They know the result, but they cannot mention because Then, what is V R1? Where is your calculator? It's a brain. It is what? 0.962 volt. This is potential drop at which point? Point what? C. This is just for you to remember. Because now, you have more than 15 testing points. So you should take safe and what? Precaution. The next one, 0.044 volt. This will be the measurement for point what? E. Are we together? Class, are we together? So we know the calculated value for point A, for point O, for point C, for point E, for point G, for point what? P. Right? What do you still need? Point D, point F. And point what? H. Then this part I will leave at the homework for you. And I know that you like homework as long as you are tired. Okay. So then let us go to the 8th step. So the 8th step now, let us compute first I2. Do you agree? Can you speak English? This one? 0.9435. Others? What do you say? So it's wrong. Thank you very much. Others, you just say wait until somebody say, and then you say yes. 0.9? 0.9 what? 4, 3. Yes, I need 3 decimal places. Is it correct now? Pardon? Okay, 0.944. Means the first decimal point it is 5. So you approximated. Fine. How do you get I2? Simple, right? Hello, your neighbor. Hello. So how? We just simplify life. Recall first Kirchhoff current law. You remember it? That the algebraic sum of the currents enter the junction is equal to the algebraic sum of the currents leave the what? So I is equal to what? I1. plus what? I2. Right? What are we looking for? I2. I2 is equal to what? I minus what? I1. And what is I? I was 9.8 milliampere. 9.8 milliampere. And I1? 1.85 milliampere. Then I2 is equal to what? I2 is equal to what? 7.97, 7.97. 95. Okay, just the 2 decimal places is enough. Milliampere. That is I2. So I2, this is the measured parameter at which point? Yes, let me remind you because I love you so much, my student. How many points remain in the first network? Only 2, VROT, VRR2 and the VLO2. Then we'll duplicate this stuff as a bongo man. But remember that the resistances are different. So you have to be careful. Because others will say, because here we have lamp and resistance is 24. Here also the VLO1 actually will be equal to VLO3. Well, that is wrong. Because we usually in Bongolan we like to simplify. For instance, now I'm doing the calculation for you, you enjoy, because I am the one who is using what? My thinking and my energy. But when you be asking to do the same, you say, I'll do it during the midnight. Can I clean this part? So now we just have 2 points, which is point D and point OT. Class point D and point OT. A. Point D and D, point F. Right? So 9 step. Let us compute OT. Compute OT. A. VRR2 and OT. VLO2. VLO2. VRR2. VRR2 is equal to what? I2 times what? R2. What is I2? 7.95 exponent negative 3 ampere multiply R2, which is what? 1.1 exponent positive 3 ohm. What is VRR2? 0.79. 0.79 what? 5 volt. Is it true, students? No. Okay, give us your reading. This is Bongoland. Same calculation, different result. It's correct. Others, what do you say? Loveness?
8.745.
8.7? So it's not 0. 24, 100. Okay, thank you very much. Thank you very much. Clap your hand for yourself. Clap your hands. You know that in Bongoland, to correct a teacher, it is illegal, In Bongoland, students trust that teachers are always correct, while we are the human being. So for me, I'm happy for the students to correct me. So congratulate yourself, because that is abnormal in Bongoland. 1, 2, 3. Hongera. Imara. Wow. So the resistance is 100 what? Oh. Then the voltage is what? So it will come what? 0.7, 795 volt. Simple. This is 1,000, so it means 100 over 1,000, 0.1. Multiplied by this one, you just see. We turn 1 decimal points, the result is that one. You don't need even a calculator if your mind is fresh. Not now. Now you are tired. Point 20? Yeah, my friend here reminding me. That is a calculated values at which 20? D. At 20D. Tell your neighbor we are at 20D. Because possibly your neighbor might be at 20A. And do you know the prayer of your neighbor? To end the class. That's the prayer of what? Of your neighbor. So your neighbor is very angry to see that we still have time. But that is accidentally. Your neighbor's heart or soul is actual to learn, but your neighbor's flesh is to end what? The class. VLO2 is equal to what? Japhet. VLO2, give me the formula. Japhet. Give me the formula for VLO2. I are 2. You just meet somebody tell you I are 2. Current 1 multiply by, do you have resistance 2? Current 2 multiply by R LO2. Right? Sorry. This makes what? 97.95 exponent negative 3 multiplied by what? 24 ohm. What is V across LO2? 0.191 volt. So this is point T. What the names of this point T? Point F. So we have the reading, we have the measurement parameter, or we have the calculated value for point A. So let us say together, say point A, point B, point C, point E, point G, point P, point H, point F, point D. So what will be your homework? Point I, point J, point K, point N, point M, point L. So how many points will you do as your homework? 60 points. So ask your neighbor, will you enjoy this homework? So this is actual homework. I'm about to end this workshop. Homework what? Homework 9. Say homework 9. Say homework 9. So homework 9. So calculate. Or simply it means that calculate measure the parameters at point 20. To remind you. K, N. Right? Then M and what? And L. That's your first homework. Look here on the blackboard. This is question 1. We go for question 2. Right? Question 2, you have to draw what? Table of calculated and simulated what? Result. How many columns are we going to have? 4. The first one is what? The first one is called what? Testing Testing, plural, testing points. The next one is what? Calculated. For example, testing point A. What the calculated value? It is 12 volt. Right? Yeah. Testing point B. What is what is calculated value? Testing point B. 9.8. But you just write clearly as how we've done it in the previous table. Right? Yeah. Then we have what? Measured what? Measured parameter. Say measured parameter. And here we are going to have what? Simulation what? Values in each point. So how many points do we have in total? Hello, the man from Mji Kasoro Bahari. How many testing points do we have? 16, So we are going to have how many measuring instruments? 16 measuring instruments. So if you do remember, we've been drawing a circuit or a simple symmetric circuit where we have almost 3 measuring instruments. But once we'll be implementing this schematic circuit, we are going to have 16 measuring what? Instrument, which practically it's not easy for you unless you use one measurement, you measure, you record. You measure, you record. But the goodness of simulation, you will have all the 16 measuring what? Instrument. Class, are we together? Is it clear? Did you understand? Ask your neighbor, did you understand workshop 9? Did you understand workshop 9? Did you understand workshop 9? Yeah, so this is the end of workshop 9. I would like to invite you in workshop 10, when we'll be simulating and having all and filling the whole table. Right? That's all. That will be about workshop 40, because we want to see and then draw the conclusion. How the calculated values relate with the simulated values. So in next workshop, we'll be simulating this schematic circuit diagram. We'll be measuring different electrical parameters at different testing points. And also we'll have a table of result. Then we'll draw the conclusion about how the calculated values or theoretical value relate to simulated values. To see the fact. If there is any relationship or there's no any relationship. Are we together? Okay, well, so for the, let me say that this is the end. Do you have any question about what we've been discussing? Do you have any question? Maybe next time, You have a question? How can we conclude values related to the simulated value? Are not related. We will see it in the next workshop. So make sure that you don't miss it, because we'll have the simulated values, and then we'll verify it, or we'll conclude. Right? Yeah. So that's the end. Thank you very much. Did you understand? Always I appreciate my students if they understand. I don't know if my students, they do appreciate me, but for me, I'm not jealous. I always appreciate people who understand what I've taught them. So let me appreciate you. Let me congratulate even those latecomers. Even those latecomers. Even those latecomers. 1, 2, 3. Hongera. Imara. Wow. Thank you very much. I love you so much. Welcome in workshop 10. Make sure to do the homework. So in the next workshop, we'll be filling just the one column. Make sure that you get connected and access this content and ask you questions in case you have one. Thank you.
Mungu ibariki Tanzania, dumisha uhuru na umoja wake kwa waume na watoto. Mungu ibariki Tanzania.